The transition to 5G has created a mathematical crisis for telecom operators. Delivering next-generation speeds requires an absolute explosion in physical hardware and capital investment. Operators are forced to acquire massive new spectrum blocks, execute aggressive network densification strategies, and completely rip and replace legacy core infrastructure. This chart illustrates the industry problem. We see a flat, stagnant line representing global revenue growth, and it is violently intersected by an exponentially rising curve representing capital and operational intensity. The sheer volume of data and the complexity of these new networks mean traditional manual cost management cannot keep pace. Human engineers simply cannot optimize millions of configuration variables fast enough. Reversing this trend requires shifting the burden of network management away from human limits and toward an automated, AI-driven architecture. Solving this financial squeeze requires dividing the telecom cost problem into two distinct algorithmic domains. First, we have spatial and hardware efficiency. This governs capital expenditure, or CapEx, exactly where you place your physical assets. Second, we have temporal and load efficiency. This governs operational expenditure, or OpEx, how you run those physical assets over time. The models required to solve the physical constraints of infrastructure planning operate differently from the machine learning systems designed to manage real-time fluctuations in load. Mastering this dual-domain approach enables operators to align their entire cost structure with actual network utilization. Let's look closely at the CapEx domain. At its core, capital optimization is a spatial problem. Every new cell site represents a massive upfront cost. Instead of guessing where new towers should go, AI-powered digital twin technology simulates hundreds of configuration scenarios. These models ingest traffic forecasts, demographic trends, and capacity constraints to test outcomes before physical deployment. By analyzing this data, machine learning identifies exactly where operators can redirect traffic by reusing existing capacity, avoiding the need to construct new sites. Industry analysis from McKinsey notes that operators can repurpose approximately 25% of their existing assets, deferring new network builds by 10 to 15%. The inverse strategy is equally vital: data-driven network decommissioning. Algorithms automatically pinpoint aging hardware and low-usage sites that can be systematically shut down, reducing the ongoing cycle of hardware refreshes without leaving any gaps in service coverage. By simulating the entire landscape, CapEx AI ensures every piece of infrastructure is mathematically justified before a single dollar is deployed. This spatial precision extends beyond physical cell towers and directly into the core network's data centers. Here, operators deploy network functions virtualization and software-defined networking, supercharged by AI. The AI analyzes workload patterns and dynamically multiplexes resources, fluidly shifting compute power exactly where it is needed in real time. Because the models accurately forecast capacity requirements, the system can scale proactively. This eliminates the costly, traditional practice of buying excess hardware just to handle occasional traffic spikes. Intelligent virtualization shrinks the physical hardware footprint inside the core, deferring massive capital upgrade cycles for years. Now we pivot to the second half of the matrix, operational expenditure. OpEx optimization targets the real-time management of temporal dynamics and shifting network loads. This chart outlines the primary operational cost categories for telecom networks, demonstrating the financial strain of ongoing system maintenance and operations. Energy consumption sits at the top, representing roughly 35% of total OpEx. Within that category, the radio access network is responsible for between 60 and 70%. Every unscheduled repair means rolling out trucks, spare parts, and technician crews. Predictive maintenance algorithms solve this by monitoring continuous sensor data, tracking equipment health and environmental conditions to spot deviations from normal operating patterns. By predicting hardware failures before they result in an outage, operators achieve an immediate 20 to 30% reduction in emergency truck rolls. This temporal control is further enhanced by self-optimizing networks. These systems operate as closed loops. They autonomously tune antenna tilt, transmission power, and handover thresholds in response to real-time conditions, entirely removing human intervention from the process. Industry benchmarks show that automated parameter tuning recovers 20 to 30% of the efficiency losses typically caused by manual, suboptimal configurations. Operational management moves away from reactive firefighting and becomes a proactive, automated system. When precise spatial planning seamlessly integrates with real-time temporal load balancing, the underlying infrastructure achieves complete zero-touch operations. Automated anomaly detection identifies subtle performance degradations, resolving network issues before they trigger a customer complaint. In the back office, AI agents process capacity requests and provisioning in minutes instead of days, reducing support headcount requirements by 30 to 50%. By integrating spatial and temporal AI, operators run their infrastructure as a dynamically scaling, self-orchestrating asset.